Hello and welcome to the last video lesson for unit number 2, and the topic is simple harmonic motion. Goal today, I want you to be able to explain and provide examples and solve real-world problems that relate to simple harmonic motion. So what is simple harmonic motion? Any motion that obeys Hooke's law is called simple harmonic motion. With respect to springs, so simple harmonic motion, so SHM, occurs in the following steps. So we have an initial force that stretches or compresses the spring. So this is you pulling on the spring, similar to what you did in the lab. And what that does is it creates elastic energy. Step number 2, the mass moves in the direction toward the equilibrium point. So now the elastic energy is being converted to kinetic or transferred to kinetic. When the mass reaches its equilibrium point, either the kinetic or gravitational potential energy, so if it's a hanging spring, carries the mass past the equilibrium point. The spring reaches maximum extension or compression length from step number 1, and the process returns back to step 2 and repeats indefinitely in an ideal system. So what I want to do is just provide a quick little diagram to help you out with that. So there's the 5 stages. I'm going to number them similarly. So in step 1, we're going to stretch this spring out. So here I'm going to do a horizontal spring. There's my wall that it's connected to. So we extend the spring out to a certain point. Here is its rest position, the equilibrium. So we'll just mark that as equilibrium. All right. And what we've done is we have provided elastic energy because there's our delta x. So step 2, the mass moves toward the equilibrium point. So I guess I'll move horizontally here. So here's phase number 2. Again, spring at the wall. And now it's reached the equilibrium point, let's say. And the direction of motion is to the left. So if we go back for 1 second then, at this point here, elastic energy is a max. Okay, and in this case, because we're moving horizontally, kinetic energy is 0. As we move then, a nice little bubble, move here, when this mass gets to the equilibrium point, elastic energy is now 0. It's its rest position. All right, and your kinetic energy is now equal to the max value. All right, so it has now reached its maximum velocity. So when it enters phase 3, what's going to happen is the spring is going to continue in its motion, and it's going to compress based on how much energy it was provided. So then we get the compression, and here's my equilibrium point. And in an ideal or perfect world, this should also be equal to delta x. At that stage, again, the elastic energy is now a max, but it will be the opposite sign because it's compressed energy. The energy's in a compressed stage. Ek is 0. And then the process will repeat. So in stage 4, what's happening? Well, the compressed spring pushes out on itself, or that energy is pushed outward, and it returns back to that equilibrium state, but the motion is now to the right. And just to be consistent here, elastic energy is now 0, and Ek is back to its max. And this is true if you turn it the other way around. Instead of Ek, we'd be looking at Eg would be involved as well. There'd be an Ek and Eg. So horizontal is a little bit easier to visualize and analyze. So there we are. Moving along. We want to find a relationship with Newton's second law and Hooke's law that we talked about in an earlier video. So we know that Newton's second law is the FU law. Unbalanced force equals mass times acceleration. We know Hooke's law, the force due to the spring is negative k delta x. Actually, I'm not going to bother with the vector notation there. If we set unbalanced force equal to our spring force, then we end up with a formula that looks like this, where we can find either any of the possible variables, I guess. We can find delta x, which would be equal to negative mass times acceleration over k, or you can find the spring constant, or whichever. So, in all honesty, you're probably better off having this formula. Then you don't have any fractions, and it's a little quicker solving for what form you want. But use that equation then to solve any further questions. Okay? So there's our relationship with Newton's second law and Hooke's law. If we're dealing with a pendulum, okay, so a pendulum is a different situation. So your pendulum will swing to its alternate locations back and forth. So the solid dot is the actual location. Okay, so the pendulum is moving in that type of motion. We can apply Hooke's law to it as well. So we know Hooke's law is negative k delta x. So that's for a spring. A spin, which is kind of like a spring. And we can change the formula such that it's negative k with a capital A, and A is your amplitude. So there's your pendulum, comma, where A is amplitude. So anything that oscillates, Hooke's law, can be applied to. So if we talk about the total energy in a system, we're looking at the total energy at the beginning of this process using conservation of energy. It's the energy at any point within. So if we're looking at that example that I had on this page at the bottom that I sketched out, it was a relationship of elastic energy versus kinetic. So that's how I'm going to set up this formula. 1/2 mv squared for the velocity of the object at the end of the spring, minus, because it's negative k, 1/2 k delta x. Oh, and it should be squared, because we're looking at energy now. And that's going to equal 1/2 mv squared prime minus 1/2 k delta x prime squared. All right, so it depends on the extension there. All right, so we can have that particular relationship in that. So let's look at an example here. So we have a spring with a spring constant of 80. So I know that my K value, just write that down, is 80 newtons per meter. There's a 1.5 kilogram mass connected to my spring. The block is pulled out 50 centimeters, so I know my delta, and I'm going to work in meters, so 0.5 meters from its equilibrium position. So answer the following, and we're going to assume there's no friction here. What is the maximum acceleration of the block? Well, remember, when we compare Newton's second law with Hooke's spring constant, we had this relationship right here. So we can just directly figure out the acceleration, because the unbalanced force is going to be the force of the spring. So setting that equal, we get 1.5 A equals negative 80 multiplied by 0.5. And we get an A value of negative 26.7 meters per second squared. And that's going to be toward the to equilibrium. Shorten that up. And we got the appropriate therefore statement with that. B part. B over here. What is the acceleration of the block at the equilibrium position? Well, we can still use the same formula. Some of you will be saying, well, isn't that kind of obvious? And for some people it will be. But when we think about it, when you see the formula, it helps sort of support that instinct that you have. Mass is 1.5. We're looking for acceleration, negative 80. And what is delta x at equilibrium? Well, it's 0 meters, okay? So for this formula to be balanced, that would mean that acceleration would have to be 0. So this is where you have a negative acceleration you hit equilibrium, so you're slowing down, and now you're going to start speeding up. So that's the right way to say it. As you're moving, let's say we extended the spring from location 1. Here's equilibrium, there's the compression. So you're going to have a negative acceleration, which is going to change every time your delta x changes. So your acceleration is continually changing throughout this ordeal until it reaches this equilibrium point where it would reach 0. Now what happens? You would speed up. Sorry, your acceleration, we're talking about acceleration here. So acceleration decreases when it gets here. Now acceleration changes direction because now you're starting to slow down. Okay, so it become negative value. All right, so put the appropriate therefore statement in there. Therefore, acceleration is 0 meters per second squared at your equilibrium position. C, what is the speed of the block as it returns to the equilibrium position? So we're looking for speed. I'm just going to leave it as V as the unknown. So in this case, we can use our kinetic, or we can use energy to solve this problem, because we know when we extend that spring out, EE, it's going to be our total energy. When we get to the equilibrium position, we know it's all been converted to EK. So in this case, EE, we're just basically setting the total stored elastic energy equal to our kinetic energy. So from our formulas then, we know that EE is negative 1/2 K delta X squared. We know the kinetic energy is 1/2 mv squared. The 1/2s will cancel. So I want to find V. So that means that you can rearrange this or you can plug the numbers in at any point in time. You have negative K delta X squared over your mass. So negative 80 delta X squared in this case was your maximum extension over the mass, which was 1.5. So when you go ahead and do that calculation, you end up with 3.7 meters per second. All right. So in this case, we'll say it's going left. So therefore, velocity at equilibrium will be 3.7 meters per second. So we're combining our forces and our energies together here in order to solve associated questions. Last one, D. What is the total energy for this system? Well, total energy for this system, we can take it at any point. So ET will equal EE, and that would be at max. So I'll just put at max. Or it's equal to EK, again at max. So if we go with, it doesn't matter which one we use here. If we use the elastic energy, EE, we'd have 1/2 K delta X squared. So we plug that in, 1/2 80 0.5 squared. We get a total of 10 joules of energy in this system. So therefore, a total of 10 joules. All right. So there we go. It's like grade 11 all over again with energies being equal and balancing. It's just in a different motion using some different formulas. Hopefully finish up in the next video. So we'll see you in a second.